In 1938, General Motors had a locomotive engine that was destroying itself. The Winton 201A had been their flagship diesel prime mover, and its pistons gave out between 50,000 and 100,000 miles of service. That sounds like a reasonable lifespan until you understand that a freight locomotive in heavy mainline service covered that distance in under a year. The Union Pacific was replacing engine internals on some 201A units twice a year. The Milwaukee Road had filed reports describing power assemblies that were mechanically worn to scrap tolerance before their locomotives had run a round trip from Chicago to Seattle. Railroad maintenance supervisors across the country had filed the same reports: premature bearing wear, crankcase failures, thermal cycles that ground precision tolerances into shapes nobody had engineered for. Steam held every major freight corridor in America, not because steam was superior on paper, because diesel could not prove it was better than mediocre. The question facing General Motors in 1936 was not how to improve the 201A. Eugene W. Kettering, chief engineer of the Electromotive Division and son of GM's own head of research, decided the 201A could not be improved. It had to be replaced entirely. The project he started that year would eventually power more than 20,000 American freight locomotives, kill 90% of North American steam within 2 decades, and build the engines that drove Allied armor ashore at Normandy before a single railroad manager knew the design existed. If the 567 engine was truly the weapon that ended steam, why did the factory that built it spend most of 1942 making warships instead of trains? 3 numbers before the answer. The 567 displaced exactly 567 cubic inches per cylinder, a number larger than the total displacement of most civilian automobile engines of the era, and the straightforward origin of the engine's name. Its pistons survived 400,000 to 500,000 miles of service in standard operation, a 10-fold improvement over the engine it replaced, with one documented unit confirmed at 1 million miles before its first overhaul. When EMD sent the first 567-powered freight locomotive on a nationwide demonstration tour in November 1939, it covered 83,764 miles across 35 states on 20 Class 1 railroads in 11 months, climbing grades that had required double-headed steam, consists while burning half the fuel. At the end of that tour, railroad executives who had spent their careers running steam locomotives wrote checks faster than EMD could build locomotives to fill the orders. None of that happened by accident. Eugene Kettering issued one instruction to his design team at the start of the 567 project: build from a blank slate, nothing carried over from the 201A. Not the cylinder geometry, not the lubrication architecture, not the block casting approach, not the crankcase depth. Each and every component of the 201A was replaced with a new design, Kettering told the American Society of Mechanical Engineers in 1951, adding with characteristic flatness that even the dipstick. The decisions that followed were precise and deliberately interconnected. The 201A had used a 60-degree V configuration, which produced an engine too wide to fit comfortably inside the narrow hood of a road switcher locomotive. The 567 used 45 degrees, narrower, taller, and essential for a locomotive format that Kettering had already calculated would eventually replace cab unit freight diesels across the entire industry. He was designing for a locomotive concept that did not exist yet. Forced air induction used a roots blower at low throttle and a turbocharger at high-speed operation, a dual-mode system that gave the engine full induction efficiency across its entire power range without the lag that had made earlier turbocharging approaches unreliable. Unit injectors, patented by General Motors in 1934, gave each cylinder precise fuel delivery without the common rail failure points that had plagued competitors. A uniflow scavenging system with 4 exhaust valves per cylinder head cleared combustion gases cleanly instead of recycling them into the next compression stroke. The 201A's designers had known about most of these problems. They had not had a Eugene Kettering. The 567 engine went into production in 1938 for passenger locomotives. By 1939, Electromotive had installed it in a 4-unit freight locomotive demonstrator they called the FT, and on November 25, 1939, that locomotive rolled out of Grange, Illinois, without a press announcement, without fanfare, without a single advertisement. EMD's own tone was precise. "We'd like you to help us find out just what we've got here." What they had was a machine that pulled tonnage up mountain grades where double-headed steam consisted with a standard operating procedure. At speeds the steam locomotives below it on the schedule could not match, while burning fuel at rates that made every mile of operation cheaper than any steam alternative on the market. Western railroads in particular had a specific problem. The 567 addressed for the first time, steam locomotives needed water. Desert corridors through the Southwest had required water towers every few dozen miles, a permanent capital infrastructure cost embedded into every freight route across the Rockies and the Sierra Nevada. A locomotive the size of a freight diesel carried its water needs in a single tank. The FT needed no water towers at all. Railroad managers who had operated steam their entire careers watched the Demonstrator complete runs that would have required 2 steam locomotives in tandem, and they ordered FT locomotives before the tour ended. EMD's order backlog was full by 1940. Then the federal government arrived. In January 1942, following America's entry into the War Production Board established formal control over industrial production priorities, directing manufacturing capacity toward military use. Naval vessels outranked railroad locomotives. Diesel engines for wartime ships moved to the top of the national production queue. The Electromotive Division halted all FT locomotive production for 6 months in 1942. The factory at Grange, by then the largest locomotive production facility in the world, stopped building trains and built Navy engines instead. 2 different Navy programs ran simultaneously at Grange during this period. The first was the 16284A, a 16-cylinder radial engine that engineers called the Pancake for its horizontal orientation inside a 110-foot coastal subchaser. Charles Kettering's own research team at the General Motors Research Laboratories had developed the prototype beginning in 1934. The Navy had approached General Motors with a specific requirement: 1,200 horsepower in a package compact enough to fit inside the engine room of a small patrol vessel. 2 164A engines were installed in each of 253 subchasers built for American coastal defense. The Electromotive Division built them by the hundreds in a dedicated wing inside the Grange plant that engineers referred to as the Navy Building. The second program was the 567 itself, modified. A 12-cylinder version, designated the 12 to 567 ATL for Atlantic tank landing, was rated at 900 horsepower and engineered for continuous operation inside a landing ship tank. The flat-bottomed assault vessels designed to drive their bows directly onto contested beaches, open their front ramps, and disgorge tanks and armored vehicles directly into the surf. The first 12-567 ATL engine was tested at LA Grange in July 1942. The first production landing ship tank was accepted by the Navy in October 1942. By June 1944, more than 1,000 landing ship tanks had been built and deployed. Each carried 2 567 series engines, the same 45-degree V angle, the same per-cylinder displacement, and the same roots blower at the base of the engine that Eugene Kettering had specified in his Blank-Slate design brief. 2,567 series engines were on D-Day ships before a single American locomotive manufacturer understood what that meant for the post-war freight market. From late 1942 into early 1943, 3 simultaneous Navy contracts had brought locomotive production at Grange virtually to a stop. EMD's competitors, Baldwin, Lima, and Alco's steam division, had been directed by the War Production Board to continue building steam locomotives and diesel switches. They had no equivalent Navy programs. They had no batch production experience at EMD's scale. They could not develop the mainline road diesel products they would need to compete when the war ended. When it did, every Class 1 railroad in America had been on a waiting list for FT locomotives they could not receive during the war years. EMD re-entered the civilian market with 4 million square feet of factory space, a manufacturing workforce trained on wartime production volumes, an engine refined by thousands of Navy production units, and a post-war order queue that stretched years into the future. They also acquired Plant 3 in Cleveland, Ohio, a former U.S. Navy wartime production facility previously operated by GM's Cleveland Diesel Engine Division, and opened it for locomotive production in 1948. The factory that had built warships was now building the machines that replaced steam. By March 1950, 392 ex-Navy 12-567 ATL engines, removed from decommissioned LST ships and sold at government surplus, were running commercial tugboats, towboats, and dredges along both coasts. Zidell Explorations on the west coast and Boston Metals on the east had been pulling engines off scrapped LST ships and selling them as industrial power plants for years. The Navy's war surplus had become the engine of American peacetime commerce, literally. On American railroads, the numbers arrived at a pace that caught even EMD's own executives off guard. The GP9, EMD's general-purpose road switcher, powered by 567 engines, the locomotive that replaced everything, was produced in over 4,100 units between 1954 and 1963. By the mid-1950s, 90% of North American steam locomotives had been retired. A fleet built over 120 years, more than 160,000 steam locomotives, representing the accumulated capital investment of every major American railroad, was functionally obsolete within 15 years of the 567 entering heavy freight service. The steam locomotive industry's response was to keep announcing that diesel would never completely replace steam, right up to the month it already had. The final steam-powered scheduled freight run on a major American Class I railroad happened in 1960. Steam had outlasted 3 earnest industry predictions of its own survival, which may be the most dignified exit available to a technology that was already beaten. More than 20,000 locomotives ran 567 engines across those 2 decades. The engine's immediate successor, the 645 introduced in 1966, shared identical external dimensions. The 710, which succeeded the 645 and is still in production today, shares the same dimensions. Eugene Kettering's 1936 Blank-Slate decision has run commercially uninterrupted for nearly 90 years. The flaw inside the strength was not in the cylinder. It was organizational. The wartime production advantage that gave the Electromotive Division, EMD, a post-war monopoly, eventually became the condition that made them stop competing. A company that held more than 70% of the American locomotive market for 3 consecutive decades had no structural incentive to reinvent an engine that was winning every contract it entered. General Electric had been building industrial turbines, generators, and electrical systems since before EMD's predecessor company had its first corporate meeting. In 1956, General Electric entered the full-scale road locomotive market with a new product line. EMD's engineers and executives, operating inside a company that had never lost a significant market share contest in living memory, treated the entry as a temporary disruption. By the mid-1980s, General Electric had overtaken EMD in North American locomotive market share. The same manufacturing inertia that had made the 567 dominant, the capacity to build locomotives faster, in greater volume, and at lower unit cost than any competitor, had produced an institutional culture that was better at defending the existing design than at developing what came next. The flaw was not in the crankcase, it was in the boardroom. Eugene Kettering retired from EMD in 1960, the same year the last steam freight locomotive made its final scheduled run. He did not live to see General Electric take the market that his engine had built. What he left behind was an engine with a documented piston lifespan of 1,000,000 miles, a design whose external dimensions have not changed since the Blank-Slate project that began in Grange in 1936, and a question nobody thought to ask at the time. What happens to a company that builds the weapon that ends a war and then mistakes the silence afterward for safety? The 567 is still running. In Navy tugboats repowered from LST surplus. In industrial generating sets. in tourist railroad switches that outlasted the companies that ordered them new. The same displacement, the same two-stroke cycle, the same 45-degree V-angle that Kettering specified to fit inside a locomotive concept that did not yet exist when he made that decision. 90 years later, the industry has not found a reason to replace it.